4.5, and now we finally get to the meat. Find the real videos, the real zeros of a polynomial function. Find the real zeros of the polynomial function f of x equals 2x cubed plus 11x squared minus 7x minus 6. Okay, so pretty general polynomial function. It is higher degree. It's just a nice little cubic function. Write f in factored form. So two things we have to do. We have to find and we have to write in a certain way. Well, this is an opportunity for Sullivan to get in some theory that, so anyway, we want to use the theorem that says that the maximum number of zeros is the degree of the function, which is 3. And so when we go after these zeros, we know that we're not going to get any more than 3. And then there's Descartes' rule of signs, and well, let's see, positive to positive, positive to negative, that's 1, negative to negative, that's not a change. So there's only one change, positive to negative, and so evidently there's just going to be one positive real zero for this function. And if we do the same thing with f of negative x, we get one sign change, negative to positive, not a sign change, positive to positive, one more sign change, so 2 total, positive to negative. So it's going to be 2 or 0 as far as the negative zeros go. 2 or 0. Okay, so now we kind of know what to expect. Sullivan says, step 3, if the polynomial has integer coefficients, which it does, use the rational zeros theorem, that any rational zero will be of the form factor of the constant over factor of the lead coefficient, to identify those rational numbers that potentially, according to the theorem, not actually, but potentially could be zeros. Use the factor theorem, he says, to determine whether each potential rational zero is a zero. Now, these potential rational zeros, if you run the, if you get your p's and your q's and your p over q's, your p's will be factor of the constant plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And your q's will be plus or minus 1, plus or minus 2, factors of the lead coefficient. And if you make all possible fraction p over q, this will be the list right here. 12 numbers, plus or minus 6 absolute values. We have 12 numbers here, and so those are the only 12 possibilities as far as a rational zero is concerned. Now, of course, the problem says find real zeros, and so we could have irrational zeros, which would not be on this list, which we would have to go get a different way. But of the rational ones among the 3, they have to be on that list. Use the factor theorem to determine whether each potential rational zero is a zero, actually. Not just potentially, but actually. If it is, use synthetic division or long division to factor the polynomial function. Repeat step 3 until all rational zeros of a polynomial function have been identified. Okay, so really what we could be doing here are 12 problems. We got 12 numbers here, and we would have to check in one way or another whether it is actually a zero. And that is a way to do it, just to go right to the synthetic. Synthetic division is so quick and easy. Some people just don't mind going right to it and doing 12 of those if necessary. Probably won't take that many before you get 3 to determine what the rational zeros are. But why not do this? Why not get a hint from the graph about what these zeros might be, and maybe eliminate some so that we wouldn't even have to check it. We wouldn't even have to run the synthetic. Of course, zeros are represented on the graph as x-intercepts. And here's a graph of f. Okay, there's f right there. And I'm using desmos.com online graphing calculator, which I recommend. And here's a 0 and an x-intercept. There's another x-intercept. There's another x-intercept of the graph. So apparently there are 3 x-intercepts. And so all 3 zeros are real. They may or may not be rational. Now let's get a better look at this. So one potential rational zero is -6, because there's an x-intercept at -6. And -6 is on the list. So we're definitely interested in this one right here, -6. -1/2 seems that it might be one of them, and -1/2 is on the list. So we'll definitely be checking that. It's not enough, of course, just to look at a graph and say, yeah, the other one is 1. It's not enough to say, well, there it is on the graph. Okay, it's a 0. But we have to verify it, obviously, algebraically. This is math class, so we have to do that kind of stuff. And but that said, we do kind of feel like we've got all 3 of them already. And with the accuracy of today's graphers, we're virtually certain that we already have the 3 real zeros. Okay, so with that hint from the graph, we would just try those 3 numbers, 6, -1/2, and 1. Doing it the old-fashioned way, if you don't have a grapher, maybe you forgot your graphing calculator and it's test day and you can't get another one, although there are resources that might be available. In the absence of that, Sullivan says, well, let's just try 6. We will test 6. Why he picks 6 out of the list, I don't know. It's very arbitrary, and well, that's what they have to do, because they don't want to take all the slides in the presentation it would take to test 12 different numbers. So we're going to test the 6. We're going to do a synthetic division with 6 and coefficients 2, 11, -7, -6. As I said, synthetic division is fast and easy, and it'll tell us whether 6 is a 0. So we bring down the first number, 2, and we begin a process of multiply and add, multiply and add, multiply and add. Multiply the 6 and the 2, get 12. write that number here and add. You get 23. Multiply the 6 and the 23, and you're going to get 138. Write that here and add 131. And multiply the 131 by 6. I'm thinking that's 786. And add, and you get 780 as the remainder. And of course, by the remainder theorem, that is f of c. And that's not equal to 0, meaning that if you do this division, division by x minus this number right here by the factor theorem, that the division does not go evenly. There's a remainder. Well, then he says, okay, well, that wasn't it. I think he just does that to show that, you know, everything you test might not turn out to be a 0. But what about negative 6? Of course, we've already seen the graph, and we feel like it is going to be negative 6. Negative 6, we'll run a synthetic with that. Same coefficients, 2, 11, negative 7, negative 6. Bring down the first thing, multiply and add, multiply and add, multiply and add, and look at that, you do get a 0 remainder. So x minus negative 6, that is x minus negative 6, that is x plus 6, is a factor of f of x. And then, you know, we could go after those other factors. Now, he's saying, so basically, if one factor of this be the x minus negative 6, that is x plus 6, then apparently f of x can be written as a product. Okay, what's the other factor? Well, it's 2x squared minus x minus 1. And so he's written the factorization here. And then you could just keep going through more of the zeros using what's called a depressed polynomial. So you've got this little one. Or you could just go after the zeros of 2x squared minus x minus 1, because any factor of 2x squared minus x minus 1 is a factor of 2x cubed plus 11x squared minus 7x minus 6. That is f of x. Well, again, we could try all of them in this little polynomial in synthetic divisions, but we already got a good idea from the graph that negative 1/2 is going to be one of them. Let's verify it algebraically. Let's test it in 2, negative 1, negative 1. And bring down the first thing, multiply and add, multiply and add, and we do get a 0 remainder. Sometimes we stack these synthetics on top of each other, right? We could have just used this 2, negative 1, negative 1 instead of rewriting 2, negative 1, negative 1, but because of the space that I had, I rewrote it. And now we have a really depressed polynomial, 2x minus 2. And, well, you know, we remember from the graph that the graph crossed at 1, so we're thinking 1 is going to be it. Of course, visualizing, just looking at this green thing here, we can tell it is going to be it. But using 1 in the very depressed polynomial 2, negative 2, which again we would have stacked on top of the other one if we had the space. Bring down the first thing, multiply and add, you got that 0 remainder. So we know we've got the zeros. Okay, the zeros are negative 6, negative 1/2, positive 1. Those are zeros. If you run any of those numbers through f of x here, you would get 0 when they come out. I mean, the easiest one to check mentally would be the 1. You know, throw 1 in here for f and get f of 1, which basically means you can just read off the coefficients. 2 plus 11 are 13, minus 7 are 6, minus 6 is 0. But that's just a check. Now, we are to write f in factored form. Okay, we know the zeros. Okay, we know we've done the first part of this, so zeros are negative 6, negative 1/2, 1, and now we have to write f in factored form. And so what we're going to do is use the factor theorem, which tells us that if a number is 0, then x minus that number is a factor. Remember that? If a number is a 0, that is if f of c equals 0, that is true if and only if x minus c is a factor of f of x. And so we'll, be alive to the fact that there could be a numerical coefficient, but other coefficients of f of x are, we're going to take all three of these numbers and subtract them from x, and those will be factors by the factor theorem. If 1 be 0, x minus 1 is a factor. If negative 6 is a 0, x minus negative 6 is a factor. That is, x plus 6 is a factor. And so basically we're changing the signs of these numbers over here. And x plus 1/2 is also going to be a factor. Well, if we multiplied all that out, would we get f of x? Well, not exactly, right? Because if you multiplied all that out, it would be x cubed plus some other stuff. But we're supposed to get 2x cubed plus some other stuff. Okay, let's throw on a factor of 2. Okay. And if we throw on a factor of 2 and maybe make this look nicer by rearranging the other factors, we can write f in factored form. So 2, let's throw this other factor with the fraction in there next to the 2. And we got our other two factors. And then partition off this part as one factor, and then we'll have our other two factors, x minus 1, x minus 6, and the other factor then will be 2x plus 1, 2x plus 1. And that, is a way to write it without the fractions, which just looks prettier. and that is the factored form of f of x. And of course we got it by using the zeros and the factor theorem. Now, Sullivan gets this factored form by factoring the last factor. Right? We got to this 2x squared minus x minus 1, and we got the zeros of it, which is kind of straightforward because you just do a whole mess of synthetics in a row and it goes really quickly. But Sullivan decides to go with factoring, and I know a lot of people are not big fans of factoring, but he does come up with the same answer. Another one, a fifth degree. Okay, so of course Sullivan's going to play with his toys here and tell us that there are going to be at most 5 real zeros because the degree is 5, and that by Descartes' rule of signs, there could be 5, 3, or 1 positive real zeros because there are 5 sign changes. 1, 2, 3, 4, 5 sign changes, so 5, 3, or 1 positive real zeros. But f of negative x, there is no sign change at all. Everything is negative, and so there is not going to be a negative 0. Well, he says because the leading coefficient is 1, 1x to the 5th, and there is no negative 0, basically we can just take the constant and, if you're going to put factors of the constant over factors of the lead coefficient, and the lead coefficient is 1, then basically factors of the constant are just all the factors, all of the potential real zeros. In other words, if you're going to find your p's and your q's and your p over q's, and q is just 1, then it's just all the p's basically. Now Sullivan is somewhat arbitrarily going to just go through the list and start with 1, okay, and it's going to work out nicely for him because 1 is a 0. If you run 1 with the synthetic using the coefficients of f, then you do end up with a 0 remainder, and that tells you that x minus 1 is a factor. And then we can use the depressed polynomial to try to get more zeros. Of course, what I'm going to do is look at a graph. I'm going to look at this graph, and what do I see? I see at 1 an x-intercept. So it seems that there's an x-intercept at 1. X-intercept at, that's a 1 right there, if you can't tell. And at 3, there's an x-intercept. But the behavior, of course, at 3 is different. So what we're anticipating, because of this behavior where it doesn't cross the x-axis at 3, it merely touches, what we're anticipating is that 3 is a double root, a double x-intercept and a double solution, a double 0 of f. That is a 0 of multiplicity 2, right? Because, just consider a simple case when we consider this sort of behavior of touching, not crossing. Okay, so let's come over here in the margin and consider, a very simple case. Y equals x squared. We all know this graph. Of course, what is this? This is x minus 0, x minus 0. So 0 is actually a 0. 0 is a 0 of multiplicity 2. And as we all know, the behavior at x equals 0 of this function is that of touching, not crossing. So it touches, it doesn't cross at the origin. And so when we see that sort of behavior, we know we're talking about a 0 of even multiplicity. Okay, so we go through our regular process. He already tried 1, and of course we saw 1 on the graph. And so we would, of course, run the synthetic with 1. And let's see, he's okay. So he got 1 is a 0 because if you run 1 in the original function f with 1, -7, 19, -37, 60, -36, and we're not really afraid of any synthetic because it's so easy and fast. Writing down the first thing, multiply and add, multiply and add, multiply and add. That's -24. Multiply and add, multiply and add, and again we get that 0. And so we know that 1 is a 0, and the depressed polynomial is 1 x to the 4th minus 6 x to the 3rd plus 13 x squared minus 24x plus 36. So we're going to run a synthetic with these numbers for the depressed polynomial. And he says, well, let's test 1 again, because you never know. 1 could be a double, even though on the graph it looked like it wasn't. It looked like it crossed at 1, but it didn't cross at 3. And so running 1 again, this time we don't get a 0 remainder, so we're done with 1 as a 0. But it is a 0 of multiplicity 1. Well, he's going to go through the list of potential rational zeros. Remember, those were all the factors of 36, basically, because the lead coefficient was 1. All the factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. So he's going to go all through the numbers in order, kind of arbitrarily. So he says, well, let's go to 2. Well, 2 doesn't work. We don't get a 0 remainder for 2. So for that reason, we wouldn't use this wannabe depressed polynomial here. We have to stay with the original. And he says, well, let's try 3. Well, 3, he says, does turn out to be a 0. Of course, we already knew that because we've looked at the graph and we saw that x-intercept at 3. And we're just going to need to confirm that algebraically. In fact, we suspect it's a double root because we have that behavior of touching, not crossing. And so, knowing that, let's see, what was that depressed polynomial? Well, I mean, we could just very easily run it again. 1 into 1, negative 7, 19, negative 37, 60, negative 36. Bring down the first thing. Multiply and add. 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 Okay, so there's your depressed polynomial. So we'll try the 3, which we know from the graph is an x-intercept in 1, negative 6, 13, negative 24, 36. And let's verify. We expect a 0 remainder. We totally suspect it because of what we saw in the graph, but you know, who knows? So we got to verify it algebraically because this is math class. Bring down the first thing. Multiply and add. Multiply and add. Multiply and add. Multiply and add. So 3 is a 0. Run it again with 3. We'll just use the numbers that we got. Bring down the first thing. Multiply and add. Multiply and add. Multiply and add. And so 3 is a 0 of odd multiplicity. You might have been thinking by now, well, there are only 3 x-intercepts, but it's a 5th degree function. So, you know, what about those other 2 complex zeros? Well, the depressed polynomial is x squared plus 0x plus 4. And so what we have is a sum of squares, x squared plus 2 squared. Well, this does not have any real 0. It has 2 non-real zeros. So we're kind of out of zeros. But the x squared plus 4 is going to be part of the factorization because we still have to write f in factored form. Okay, so you know, everything we've just done is confirming this picture that we got with a 0 at 1 and a double at 3. So the factored form is going to be f of x equals, well, if 1 is a 0, x minus 1 is a factor. If 3 is a 0, x minus 3 is a factor. If 3 is a 0 of multiplicity 2, then we got 2 factors of x minus 3 as factors. And of course that x squared plus 4. We don't have to throw any numerical coefficient on there because our lead coefficient was 1. So here's f in factored form, and I think that we have made this a little bit simpler by using the graph, letting the graph help us, and then using synthetic division instead of factoring.